Because of farming
I mean,
Okay,
yeah, it won't be
so-
this less of a simulation, but like
Last time, what did we talk about?
theoretically, the overhead.
Differential equations, what kind? Ordinary. And which first order, second order? Linear, nonlinear? Homogeneous, inhomogeneous? What do we do?
Linear and then non.
We did linear, and then we went to nonlinear at the end, which we're going to pick up. And we did both homogeneous and inhomogeneous. And the key thing to remember is in the homogeneous case, you can guess the answer. It always looks like an exponential. The inhomogeneous case, we got worried because there was this crazy complicated formula in the normal solution. But in practice, we found that things like thinking about the fact that in the long time limit, it would go to a steady state value was an easy way to get a particular solution out of the system. So it's not quite as scary in the real applications as that formula makes it look like. But we do have that formula. So for first order linear constant coefficient differential equations, we have the answer. So there is no equation of that form that we cannot write down the answer for. So that is a helpful step. Okay? So what was our nonlinear challenge problem? Radiation. Remember we had this planet that had ice on it, and so what happened when we got more ice? Icy planet. Radiation coming in, radiation going out.
More ice, supposed to be radiation.
Yeah, so we had an albedo feedback that had about the ice. And so we drew a shape that looked something like this for the radiation. Let's see, which one is this? This is incoming. Wait. Oh, I forgot which one.
Yeah, that's right.
That's the incoming radiation. So if we have hotter temperatures, we have less ice, so we absorb a greater fraction of what's coming in. And then if we have no ice, like kind of out that end, it just levels off again. And if we have a lot of ice, it also levels off again, and somewhere in the middle there's a transition. Okay, and what about our outgoing radiation? So not the reflected part, which is in this, but the outgoing long wave. How do we think about that one? It goes like this, and there was a tuning parameter for greenhouse gases, which was really the amount of water vapor you have at warmer temperatures. So it was a temperature sensitive one. And so we talked about this guy moving up and down a little, maybe being over here, maybe being over here. And so what are the right one, this one, this one? Okay, so where do we have a solution then? That's a steady state solution. How do we draw them on this figure? Our equation was the temperature d time of some coefficient equals radiation in minus radiation out. That was the simple thing, and both radiation in and radiation out were functions of temperature. That was the complicated bit. So how do I get a steady state solution out of this equation? I could set this side to 0 and it would be steady, it wouldn't be changing. What does that imply about the radiation balance? And so where is equal on this figure then? The intersection points. So here's one, here's another one, here's another one, here's another one, here's another one. And then we walked ourselves through the stability of those, in the sense that if you push yourself away from one of those a little bit, do you come back onto it, or do you go somewhere else? And we found that this was a stable steady state, this was a stable steady state, this was an unstable steady state, this was a half stable steady state, and this was a stable steady state. Remember that, all this coming back now? Okay, and then the last thing we did was we said, well, all right, these are these crazy complicated formulas with like tangents and sigma t to the fourths and like, so what do? We proposed simplifying this to get a linear system that we can solve. How do we do it?
We took the Taylor series of like the individual, or like the radiation and radiation to represent the whole thing.
Right, so we could Taylor expand this, and it's just going to be something like this. But let me be a little bit more careful. We need to Taylor expand about something. Right? We have the Taylor series, we could expand and come up with a linear form and linear approximation about any temperature. So what's a useful temperature to Taylor expand meter? One of these steady states. Does that make sense? So I could, let's just label number 1, number 2, number 3 on that branch. So I could do a Taylor series, and I'm using this little star here, which I think is what he, no, I don't. Steady state. So I could, when we had a steady state solution, I could Taylor series expand near that. Right, so I have one version of this near number 1, and a different one, prime, steady state number 2, and a different one, except I can't. Which one is 1, 2, 3? Okay, I'm gonna make this hard, much harder to put myself out here too. I've got too many subscripts. Everything's got numbers and it's getting all tangled up. Okay. Yes.
Why is that fun?
I'm just distinguishing that these numbers are going to be different depending on which one and so was trying to put the number of primes equal to the number on this, but then I screwed up and was off by 1. So maybe we can put 2 on here and 3 on here and 1 on there, and then we actually have a better system. So 1 prime is the one that goes to steady state 1. Okay? So let's assume we do that and we solve, does the steady state solution change in time? We have fixed 4 functions here. So we talked about changing the greenhouse gases. Let's forget that and just say greenhouse gases are locked. Are these changing in time, or are they just complicated formulas? Sorry, the steady state version.
Probably not, because if you look at it graphically, like this slope there is 0, so the time will be the steady state will change.
Yeah, so if we hold the shape of this function and the shape of that function fixed, we might move our time-dependent temperature around, but the intersect, so we could move around away from those points, but the intersection points would stay fixed. Does that make sense to everybody? So I can do this for free. Because if this doesn't change in time, taking its derivative doesn't matter. It is true. Both the unstable ones and the stable ones are all fixed in time. We're about to explain stable and unstable, how that appears here. And that, but I want to make, why did I do this?
it's not, you can consider like that as a variable like that.
Because now I have a homogeneous differential equation, because I have the same thing on both sides. Or I have an easy to solve homogeneous part of my differential equation. Everybody understand where that's coming from? And even simpler, so let's just, this could be any number. I could have put the number 1, number 2 right up here, but let's just focus on the number 3 one for now so that we can be concrete. What's this going to be? If I put this in here. Think about what this means. This says there's a rate of change of temperature no matter your distance from the steady state solution. But what if I set the temperature to the steady state here and here? I can evaluate this term there, and what should it be? If I'm sitting in a steady state solution, is there a rate of change of temperature anymore? No. So if I play this game of putting that part in, I now just have this one term the whole game. Does that make sense? And I can do the same game here and here, but in both of those cases, I should write it as C dt, dt, C dt, oops, d by dt, t minus t steady state 1, d by dt, t minus steady t steady state 2, d by dt, t minus t steady state 3. So I've got 3 approximate differential equations. 1 at each of our steady states in the neighborhood of steady state. What kind of differential equations are these? Set the constants to 0. So I should remove this part. I said, let's take the steady state and suck it in here. And we can do that because it doesn't change, it doesn't depend on time. So I just added 0 to this equation. Right, so I didn't really change the equation to that end. But now look at what this means. This says that the rate of change of temperature away from its steady state value is one part that depends on how far temperature is away from its steady state value plus possibly a constant. But we can evaluate the constant by just setting the temperature equal to the steady state value and asking what should happen. But it is a steady state value, so there shouldn't be a constant. So does that make sense to everybody? Yeah.
My question is, when you said you can suck in the steady state temperature because it's equal to 0,
Uh-huh.
but like even based on the graph, the steady state temperature is kind of non-zero values. So how is that? Like,
Yes, sorry, the rate of change of it is equal to 0. I haven't changed the equation by putting something inside a time derivative that doesn't depend on time. And I'm just simplifying this equation without changing the answer. Because now it should be apparent, so we got rid of all those constants, and now we just have one coefficient left. And so what kind of differential equations are these? Homogeneous, first order, constant coefficient, linear differential equations. And we could have done this almost regardless of how complicated these functions were every time. So if we tailor series in the neighborhood of a steady state, we're going to get a really simple solution. So what's the solution for all 3 of these? What does it look like? It looks like t minus the steady state, whichever one it is E is whatever, the initial value minus the steady state, e to the something. Do I want a positive or a negative something? What's my something? going to take the time derivative of it, and I'm going to get a c divided by a c1. So I need c divided by c1 times that. Because we want to stay linear, because we don't know how to solve the nonlinear differential equations. It's not because we think it's accurate. We know that if you go far enough that this curve starts to bend, it's going to be a bad approximation. But basically what we're doing is we're linearizing these functions in the neighborhood of the steady state to ask what goes on just in this little neighborhood. That's a really good question. So everybody is on board with how we got this? So now we've written down our solution class, and it's true if we're talking about steady state number 1, or steady state number 2, or steady state number 3. Now, how does stable and unstable appear in this equation? What would this coefficient be if it's stable? What does it mean? As time goes to infinity, what happens? It wouldn't blow up. But what we want is we're talking about the deviation away from the steady state is some initial distance, however far you start, and over time, what's supposed to happen? It gets smaller. So this is supposed to go to 0. So this goes to 0 as time goes to infinity for steady state. Okay, so how do I make this side go to 0? This is a constant. This is a constant. This is a constant, and it's a positive constant. How do I make this thing go to 0? If C1 is negative, this will always go to 0. If C1 is positive, what happens? It goes to infinity. So, this coefficient right here, the sine of C1 determines the stability. If C1 is less than 0, then stable. If C1 is greater than 0, unstable. What if C1 equals 0? Wonderful. And the C1 equal to 0 would be this one, where it's stable on one side and unstable on the other side. And that means that essentially this Taylor series doesn't really do the job. You'd have to look at another term and figure it out, because it's the curvature that matters, not the linear part. Okay, so who's heard of a feedback parameter? Or feedback? Everybody? That's the feedback. In every system that has a linear feedback, it will be this coefficient. And if that parameter is negative, if you have a negative feedback, it means that initial perturbations damp out in time. Doesn't matter whether the perturbation is positive or negative, warm initial condition, cold initial condition, you still come back to the steady state in infinite time. If this parameter is positive, then we have a positive feedback, and it will be unstable. And an initial perturbation will grow in time. That makes sense? So people use negative feedback and positive feedback in all kinds of crazy ways and mean lots of crazy things. this is the right one to think about. This is the one that describes the way a system works. And we're going to do more complicated versions where the feedback parameter can be imaginary and things like that when we get to higher dimensional problems. But for now, this is the simple way to think about it. Does everybody see how the process works? So I take my complicated nonlinear system. I examine the steady state values by setting this to 0, and then I find the intersections between these. And I might have to use a computer or something complicated that, we talked a little about root finding. This is maybe complicated to figure out where the steady states are. But we can find them, with a computer. Now we tailor series near those steady state solutions. We play a little game with the particular solutions by hiding, the steady state values inside the definition of the variables to make our problem homogeneous. And then the 0 coefficients all vanish in that case, and the 1 coefficients are the feedback parameter. So for every nonlinear first order differential equation, this approach works. And the feedback parameters can be interpreted based on that. That makes sense to everybody? Okay. So, how do you think, before we move on to the second order differential equation, how do you think about what the feedback parameter means in this case? What is it measuring?
If it's stable, it's like
Measuring the rate of convergence to steady state. And in this problem, what makes us converge? We talked about it last time. So the dashed line is steeper than the solid line. So that means that the rate of change of outgoing radiation with temperature is greater than the rate of change of incoming radiation. So it's the relative slopes of those two things. Because this is a Taylor series for their difference. So it's like one needs to beat the other one out. So which one of these is a positive feedback and which one's a negative one, just from the physics? Like, is the albedo change a positive feedback or a negative feedback? You warm up the planet, you melt the ice, you get more warming or you get less warming? More. So we have, people do this like T plus ice minus, which then implies more T, or I guess implies radiation incoming, which implies more T plus. So that's a positive feedback. And what about the radiation out to space? There are two parts of that, which are kind of combined that we would say. So we would say the temperature goes up, which makes the water vapor go up, which makes the radiation outgoing go down, which makes it T plus. So that's a positive feedback. And then there's also a negative feedback, which is the temperature goes up, then sigma T to the fourth goes up, which makes the outgoing radiation go up, which makes the temperature go down. So it's the opposite. So it's negative feedback on that branch. Does that make sense to everybody? Sorry, we haven't defined how I'm drawing symbols or anything. But you guys have seen these little kind of flow circles and like lots of, this is a common thing to do. These I find sort of helpful, but this I find really helpful. This is the one that tells you which one of these loops wins. How do we decide what wins means? Well, we put it into a formula like this. We Taylor series and we evaluate the sign by coefficient. That's what wins means. That's the only one that counts. Okay. That makes sense to everybody? All right, cool. So this is an important idea. We're going to keep coming back to it over and over again, but it's like, it's a nice thing to think about when you're thinking about climate system dynamics and feedbacks, and it could be lots of other feedbacks too. It doesn't have to be climate related. It could be, mantle outgassing has all these kind of loops as well. So does earthquake shear resistance has these kind of things. If you break it, does it accelerate or does it dam itself back if you try and make a small perturbation? So all that kind of stuff can all be put into this framework. And the linear term is helpful. Frequently in nonlinear systems, the linear term vanishes, and then then things get more complicated. But if it does end up with the linear term dominance, you can always do this. Cool. All right. So all of the differential equations we've done so far have been first order. And so in first order differential equations, when we get to this stage, we have an equation for the sign of C being, if it's a negative one, it damps. If it's a positive one, it goes up. This thing. In a second order differential equation, something new can happen because we're going to get a quadratic equation for that coefficient. So what can happen in a quadratic equation that isn't a positive or a negative as the answer? Imaginary exponential. And if an exponential is imaginary, e to the I rate times time, what does e to the I rate times time behave like? Is it a decay? Is it a growth? It's periodic because we've already talked about e to the I theta equals cosine theta plus I sine theta. So when we get to second order differential equations, we're not only going to have the ability to exponentially decay to our steady state or exponentially grow away from it, we're actually going to be able to oscillate around it with sine and cosine. That makes sense, everybody? And the break point is the order of the differential equation. That's what the key is going to be. We're going to go through one right now and see how it works. Okay. So we talked about the hydrostatic balance last time. The pressure dz minus rho of g. And so the hydrostatic balance is here, which says that the increase of pressure with depth or with altitude goes like the density. So that was our physical point. But we said, actually, that comes from the momentum equation in the vertical direction. So if I write the acceleration, the rate of change of the vertical velocity, you can think of it as an imbalance in the pressure equation, in the hydrostatic balance. So if there was a little bit too much pressure, it would like squish stuff to shoot upwards. If there was a little bit too little pressure, the stuff might go down. Does that make sense to everybody physically? So we can imagine a little blob of fluid inside of stratification, and I guess the density would be lower above and higher below. And if I push that little blob down, it's going to be anomalous without changing its density. It would be anomalously what compared to its environment? Take it. Push it down. Sorry. This is negative, so density is lower above and higher below. Thank you. And then in the middle, it's just the middle. So this guy is somewhere in the middle, whatever. It's in the middle. If I push this down, how does its density compare to its environment? It's going to be lighter. So what do you think happens next? It's going to bounce off. If I push it up, what's it going to find itself? It's going to be denser. So you can imagine if we push this thing, it'll start bouncing. This is a first order differential equation, but we don't quite have it there yet, but we're going to get there. So if I have a background part that goes like this, where 0 equals the pressure C minus rho G. If this is my my steady state situation. That's just the kind of hydrostatic balance that we talked about last time. We went through a bunch of different problems that we could solve for this. We had ones where the pressure increased exponentially. That was the atmospheric case. We had ones where the pressure increased linearly and the density was constant. I want to consider a simpler case than either of those, which is just where the density increases linearly. Okay? So, if I set this parameter to be equal to something that I will just mysteriously call minus n squared. This is the rate of change of density with depth. Just assume that it is this thing. And it has these funny gravity in it and a density over here to help us kind of sort out what that's going to make everything cleaner. If I put that into place, then this will express this low density above, high density below. And the minus sign here is to make it so that density is increasing as we go down. And the square just to remind us that this is supposed to be a positive definite number. That makes sense, right? Okay, this thing is called the Brunt-Weissel frequency or the buoyancy frequency. It's not clear why it's a frequency yet, but it's going to be a frequency in a minute. Okay. So I need to do a little work on this equation. If I move this guy at a distance delta z, how much will the pressure change if I examine it, at location z plus delta z? I could just, let's write it down. Pressure of z plus delta z, rewriting z. I'm going to just write it out that way. So, sorry, let me draw this line. If it's not moving, how much higher is the pressure deeper down? You figure it out in this equation. The rate of change of pressure is going to be this guy, but it's kind of off by a derivative. G. So that would be the rate of change of pressure, which is related to the density at that deeper depth. Everybody see that? This is the background part. Right, so this is the part that's explaining this. And we said that we're going to come back to this in a minute. But now let's think a little bit about our anomalous displacement of this guy. How much pressure anomaly, or what kind of density anomaly is this going to exert if you move it down? If I move it down without changing its density, what will the density of that blob be? If I go to z plus delta z. It would be density of the original location, right? So if I want to examine its acceleration, go back to this equation, it's going to experience the pressure from the background part, but it'll have a density that's where it came from. Everybody see what I mean by that? So it'll have the pressure that comes from the background plus the density of its original location. And that would be the acceleration that we experience at z plus delta z.
So did if you look at the top left, there's a row. Sorry, all the way to the left. There's a row that has the WBT on the left side.
Oh, yeah, sorry. That's just perfect. And which row would it be? It would be the row of the same parcel, so it's a row. Okay, almost there. So what is the vertical velocity in terms of delta z? If I let it go and then delta z starts changing in time, how do I measure vertical velocity? Use delta z. Delta z is a displacement in space. Delta z is changing in time. What's W? Derivative. So I could write this instead as d by dt squared delta z. Right? We're getting closer. I've got my rho z. Let's move the rho z over to the other side. We're going to do another fancy thing in a second. 1 minus 1 over rho z d by dz pressure at z plus delta z. And now it's just minus g because I put that one in together. I can't stop it by moving to the other side. Okay. So we're assuming here that the pressure is like coming from the background part. But I actually wrote down what dvz was up here in terms of the background part. It's just rho of that for the background bit. So I could replace this with the rho of the background, and then I have something that looks like, I'll probably have a sign. Rho of z plus delta z over rho of z times g minus b.
So we'll just have the first step where
Oh.
what is the z data?
So I'm just saying, if we're thinking about delta z as being a displacement of our particle and w is the velocity of the particle, we would just write these down together. So the z actually isn't that important. It's the delta z that's governing how much velocity you're getting. So writing w as a function, I would want to write it, it's the function, it's the w that occurs at that location. But actually your displacement, that's having a time derivative taken of it is part of the equation. Does that make sense?
Where did the derivative go in my last step?
Sorry, let me be very clear. This is the pressure, this is the density. So I'm just converting from this background pressure into the background density. Okay, so now there's one more magical step here. So this is some potentially horrible thing, but what would happen if I Taylor series rho z plus delta z about delta z equals 0? If I Taylor series this, I would get one part that just cancels rho of z, and we have rho of z at the bottom, and then I get a part that's proportional to delta z, right? Everybody see that? The Taylor series would be a delta z of this. And actually, we wrote down the part that's going to tell us how big the delta z is. If I wanted to know d rho dz times delta z, which is going to be the term in that Taylor series, it's proportional to n squared. N squared is the coefficient that's going to come out. And what happens to those two g's? So the g from the first one, I'm saying if we do this right, it's going to be that. So plug in this formula for rho and then figure out what the Taylor series is to the delta z order that's going to be the coefficient. It's just saying the rate of change density with height is a linear thing that's governed by this linear law that we put out before. So when I Taylor series, that's going to be the coefficient on delta z. And these funny factors there were just the funny factors I wanted to make all the other bits cancel out. And then the last bit is the g out here cancels with the first term that was the rho of z over rho of z. So those will cancel. So yeah?
Sorry, can you talk a little bit over g rho over g z or how that relates to the rho z plus delta z?
Right. So I'm saying rho of z plus delta z, my Taylor series that is going to be rho of z plus delta z du rho dz plus that. And I just wrote down what d rho dz is. It's that. So that's rho of z times 1 plus delta z times minus n squared rho, the rho comes out, n squared over g. And if I take this form and plug it into the numerator, the rho of z's cancel. I get a 1, which is g minus g. And then I get this crazy term, which becomes this. Everybody see how that goes? We're playing kind of the same game. We took the right-hand side of this equation and we Taylor series around a convenient location, and we got a linear dependence out of it. Okay, so last bit of business. Now what do we do? What kind of equation have we got? We've got a second order. What kind of differential equation? We've got d squared by dt squared delta z equals minus n squared delta z. So what kind of, if n squared is constant, which it doesn't have to be, but we decided to make our lives easy to say that it was, what kind of differential equation is this? Homogeneous? Constant coefficient. Linear. Second order. Ordinary differential equation. Everybody on board? So it's homogeneous, so we don't know this for second order differential equations, but the same trick works. We can assume that delta z equals delta z initial e to the, let's just call it m times z. Oh, should this be z or t? T. So it's a homogeneous differential equation. I can just assume an exponential, see what happens. Okay, if I plug this into here, what do I get on the left-hand side? Okay, well, delta z naught is an initial condition. Sorry, so this is a constant. I'm just calling it delta z naught instead of that. So, what happens when I take the time derivative of this? It's the same thing times 2 powers of m. And the other side is the same thing. Here to here, that cancels that. Which is the minus sign. So m squared equals minus n squared. So remember I said we were going to get a quadratic for the rate part? That's what we got. But now, how do I solve this particular quadratic? Remembering that this is a positive definite thing. This is definitely a negative sign. What's m? m is plus or minus I times n. So we get two solutions. We get one plus I times n, and we get another one minus I times n. So I got two solutions because I had two roots, two possibilities. Remember we saw this a little last time? And I add them together. Why do I get to add them together? Because it's a linear differential equation. So if this is a solution, which I know it is, because that's just the plus root, and this is a solution, then I know their sum is a solution. They're both constants, and I just put a plus to remind us we're on the plus one, and a minus to remind us we're on the minus one. Would you tell me? So how do I find these constants? How did we find them last time? It is the initial value, but we've got two initial values. If I set t equals to 0, then I find that their sum equals my initial delta z0. But I don't know what they are individually yet. What can I do that would tell them apart? I could look at the time derivative initially. And then I would have a plus in delta z plus minus in delta z minus equals d by dt delta z at time t equals 0. So I need not only an initial displacement magnitude, but I need an initial velocity. And these, can we solve those two differential equations with delta z plus and delta z minus? We can. We now have a linear coupled algebra system for that. So it's just a matrix equation for delta z plus, delta z minus, delta z plus, delta z minus. It looks like 1, 1 plus in minus in delta z plus delta z minus equals the delta z t equals 0 delta z d by dt. That makes sense to everybody? So second order differential equation, we need two initial conditions, not one. And the two initial conditions we get come from the initial displacement and the initial velocity. In this particular problem. But all we had to do was, when we got to this stage, was say, oh, how do I figure these things out? Well, and if you had been given this problem in a cleaner sense rather than the rather wandering way I got to it, this and this would have been provided. I would have told you this, and I would have told you this. And then you would have known, oh, I can take the derivative and alpha. Does that make sense? So this is an example of second order, and the key difference is that when we assume our form, we get a quadratic equation for the coefficients, and that gave us two different roots, two different possible solutions. We added them together. That makes sense? All right.